Yeah, good morning. Can you hear me?
Yes, sir.
Good morning.
Okay.
Sir, good morning, sir. Sir,
Good
I have some
morning.
questions, sir.
Yeah, sure. We will have a little later. We'll discuss. Maybe today is 2 hours. You don't have any other lectures, right? In next hour. I mean, last time you said like it is for only 1 hour. What about this week? I'm just asking, confirming that this is for 2 hours or 1 hour.
2 hours.
Ah, thanks. Okay, let's start. Um, yeah, confirm that my screen is visible at your side.
Yes, sir.
Fine. Okay. Um, this is, let me look at the various things. Yeah, fine. Okay, we started this one yesterday, I guess. What is this? Okay, the matrix way of representing the neural network, and then we will proceed further. Okay. Some of you are asking questions or something, so before going ahead, I will address. Yeah,
Sir,
yeah.
regarding the analytic functions.
Okay. That is actually out of the way, but regarding the analytic functions, this one. Okay, yeah. What is the question?
Sir, if we are given an analytic function, the Taylor series is approximating well enough. So we don't need a neural network, right, for approximating analytic function.
For approximating analytic function, you're saying like you don't need a neural network.
Yes, sir. Taylor series is doing good enough work.
A Taylor series does everything actually. I said I think there is a given another one more statement after that. Yeah, this one. Even Taylor series does this job on a compact set. Even we always our problems are in the local. Taylor series analytic functions are doing in globally much good. That's what I see. Analytic functions comes in the place where Taylor series is doing is even Taylor series approximates globally for analytic functions. But even Taylor series works in the locally as well in a good way on a compact set even like you don't need to worry about the given any target function g of x. Let's say this one g of x, and in a particular region you would definitely find a Taylor polynomial which definitely approximates within this region. So to approximate any function and theoretically where you are looking at it, whether you are local or global. So our problems in nature are in the real world, not in the global sense. We always look for certain region, certain bounded domain, certain things only. There is no real problems, real life problems um, which are existing throughout the domain, like any domain RMR, and we look at some region only. If you look at whatever data you are collecting, and if you project it in any space, that is sitting inside a particular domain. It won't occupy entire Rn or RD or whatever D dimensions. It is just sitting inside a particular domain. So the analytic functions are for the sake of looking at a global sense, the nice behavior of them in a theoretical way, so that these analytic functions uh, kind of like comes a very good way of representing in the global way, so that we have a definite format for them, the sequence format or series format, so that we can do them very good. But in general, in the life, the real life approximations, for example, some data you have collected from an experiment, whatever experiment it may be, anything. I'm not quoting it, which field of the domain it is. If you try to make it learn out of that, it definitely, uh, unless that solution is following analytic format, the if that experiment constitutes a analytic solution, usually they are not analytic ones in the real life. So we don't need of particularly looking at analytic. Analytic in the sense of global sense, they work good. They have their definite formulation. The like e for x, sin x, cos x, all these are analytic functions. So you have if you ask it a approximation polynomial, you can give it immediately the series, but you cannot give arbitrarily for arbitrary functions. You cannot give such a series if it is not analytic. But in a compact set, if you then you can definitely give a series. That is, Taylor series works in the local nature. That's what this statement I made it the next day, that like this is from the Weierstrass approximation. That's you already know it. It is for any function, doesn't matter, any continuous function. It is that is the intelligence.
So, sir, why neural networks over Taylor series?
Why neural networks?
Over Taylor series.
Yeah, that's what my question for you. Like the that's you need to think of it. Like it is a lot of things to understand. So we will go slowly. I will not discuss this one at the very beginning now. We will see at the end of the course once we completely dig all the features inside. We have not explored everything inside of these features, what this F is actually doing. Then those features are really possible with this one, the tailor, that we will see it. That's what, like, it is a kind of like putting you at the beginning this question so that you can travel the thought process throughout that. How can we do the same with this tailors analogy? So you keep thought process it behind the head, back of our head when we are discussing the internal components, how learning algorithm we are developing. The same learning algorithm can we able to achieve this one with that LR, with such a uh, good way. That's the thing we will see. Like, for it's not just for simple R2 to R2 R, for anything, for any dimension, Rn to Rn to Rn, whatever, like, is that possible for to come up with a good learning algorithm with them? That's what, like, suppose if you are assuming some model or algorithmic strategy to come up with that, then how better it is, if first of all possibility is there or not. If it is a possibility is there, if there are no hurdles, theoretical hurdles, um, then that model or algorithm, how better it is than over these neural networks that we will see. If you find out something, that's what trick me now. As of now, we will proceed with this neural networks things, and you keep thought process behind, back of your head, the same lines of how we approach to approximate a function, target function. The same thing is possible, or similar things, not exactly the same thing. Is there any alternative version of producing algorithmic strategy to come up with a Taylor polynomial to approximate for any dimension? That's the thing to think of. Okay, so far, okay, I was keep discussing all these things, but now we are slowly coming out of the lines of theory, and putting into kind of in the journey of mechanics, where how what's happening inside, and looking at the matrix structures or matrix language is the one, like, we cannot code with this kind of things, like the set of continuous functions, the set of these things, we cannot code them. We need a kind of like computer language before uh, putting this stuff and try in the computer, so that we change in the language of analysis into which is feasibly understandable for computer as well. And of course, that you have to think of, is it possible for the same with the Taylor series, that the language of algorithmic format to how computers can we convert such a beautiful algorithm, where um, we can do that with the Taylor series. Okay, now, and before going ahead, all those things, think of something, another question, like, what could be Taylor polynomial or Taylor series expansion for Rn to Rn? This is also one thing, like, because the neural network, we have seen a structure, like, we can go ahead with not just with the Rn to R, we can go with the Rn to Rm. The neural network functions, we have seen that multi-layer feed-forward networks with several layers, with n dimension to m dimension, we can make the classes of these things. But is the same possible with the polynomials or Taylor polynomials, to bring this nature, and what are those formats, how complex they are, and what are the coefficients, I mean the weights or the parameters, whatever you call it. So that you think of it, like, you try to construct a Taylor polynomial from, so we take simple examples like R2 to R is the simplest one, you can do it easily. But what about this a Taylor polynomial which is approximating let's say R2 to R2. Can you come up with a Taylor polynomial or not? First of all, if you could able to come up with a Taylor polynomial of this function, which is taking R2 to R2, then we can think of letter. So you work it out. What kind of, you might have seen the Taylor polynomials of maybe uh, how many degrees you have seen so far? I'm not sure of Taylor polynomials or Taylor series for mm, from where to where. We have covered in our courses somewhere in the past, like this one or something. Could you think of these Taylor series of which takes R2 to R2? Am I audible or
Audible, sir.
okay? Okay, you are not answering, so I'm just so what kind of Taylor polynomials or Taylor series so far you have seen? Like you Taylor series from sin x, cos x, all these things you might have seen that. Whether you have seen the expansion sin of xy, sin xy, it is taking R2 to R, e for xy or e for x plus e for y.
Yes, sir. We have done them in scientific computing.
Okay, so you have done the Taylor series for 2 dimensions. Like what would be the typical Taylor polynomial expansion of x comma y? Do you know? Can you express with the summation? I think we have expanded for the single variable. Something like it goes with the two indices I and j. Yeah, you come up with, you try this one. What is the Taylor polynomial? For the two variables, and that is okay, that is possible, you are doing it, and look for what kind of Taylor polynomial for this one. And first of all, before understanding to develop a polynomial learning algorithm, now you have to study the look at all the versions of all the Taylor polynomial formulations. You should know them, then generalized way, so that you can frame algorithm. That is why neural networks, what we are doing here, no matter whatever Rn to Rn you give, you can able to come up easily. Like you give another y1, y2, y3, y4, y5, r3 to r5, nothing. You just simply come up with a some bunch of edges connecting with whatever layer choice you choose, and you come up with the same formulation. So you have a generalized formulation here to develop such a good way. But now your task is to look at like how do you come up with a generalized formulation for such mathematically. First of all, forget about computers, that is later, can be bring down to a standard format, so that later we can convert that into a algorithm. That's what my intention, that functions from Rn to Rm. That's you just explore mathematics. Okay. um, Now let's see. Okay, before going further from this point where we have stopped, I guess, like, okay, this is what we are discussing. Something, the matrix conversion we have uh, done yesterday. This is okay. So far, I have not concluded one statement I thought of conclude before here, before going with matrix, but I just wanted to conclude with what so far we discussed the dense properties of this sigma pi, or um, like we have so far what networks we have discussed. Let me recall all the things: sigma n of g, sigma n2m of g, um, what else? Sigma pi n of g, sigma pi nm of g, and these are all single layer feed forward neural networks, and multi-layer you can say sigma n of g with the layers L belongs to some k1, k2, and so on kl. Or for the similar, you can say that the multi-layer L belongs to L, capital L, I can keep it L sequence. For the feed-forward neural network of sigma pi n, for the same thing here it goes sigma pi nm of g. Maybe I may have given other versions as well. I don't remember what are all we have. I'm just remembering few of them. The several classes of these are all almost same, but slightly classified into one with other. Only the large class is this one. Guess this one. The rest, all these are like subset of this. We just need to change the parameters into it. If L equal to 1 and M equal to 1, this is the one. And yeah, if this product is only one time production, that's okay. So what are all these things? These are all dense in the compact set. And these are all sequences of functions dense in a continuous class, or you can say the measurable class in general. That's what. Now what they are saying, the dense, okay, these are all like the property which is you are approximating the norm, f of x minus target function g of x is always supernorm is come up with given epsilon, something like this. So you can achieve a function which is comes closer to your target function. That's what, like this saying, this one is the dense property, the denseness. Obviously I mostly use dense rather than going into the epsilon definition. The dense means automatically this attracts that dense definition. So that is what usually called as universal approximation theorem. Universal approximation theorem. I haven't proved this one. I don't want it you as well. Like rather than going with the lines of the theorem, it is much uh, understandable. Like if you know the proof of this one, that is enough. This one, the Weierstrass approximation theorem, I could say this one. This is, you know it already. This Weierstrass approximation, I think Stone Weierstrass mostly called in textbooks. uh, you have already covered this one. That proof, if you revise once, it is goes in the same lines, but slightly few other pieces will add up here. But the finally saying that the denseness uh, sitting inside it. Okay, I just wanted to. I'm just thinking that like how Wikipedia shows that statement, and let's say. What is that universal approximation theorem, so that like how do you understand and let's see, I'm not sure whether they have Is that right, boys? Universal approximation theorem. Okay. Yeah. Okay. This is the statement. Okay. Take a minute. Um, okay. Try to understand. I think more or less it is quite same as we discussed, but maybe the language of expressing is different. It is. It is the same thing. You look at here. Like, let me take this one. So the same whatever we have discussed the same you can see. Let uh, this one is a set of all continuous functions. From here the x is a kind of like a metric space or maybe a topological space generally, but we restricted ourselves like it is again a Euclidean Rn. But it's okay. You can consider this X as a more abstract set, even that is possible in theory. But practical, we mostly deal with Euclidean problems. Okay, denote the set of continuous functions from a subset X of a Euclidean Rn space to. Oh, okay. Again, okay, they are also considering X as again Rn only, space to Euclidean Rn. That's fine. uh, Sigma belongs to is a continuous R to R. It's a activation function. In our case, we have used this capital G circle X. This is a X is a continuous function, I guess, like yeah, sigma of F or sigma of this function Xi, sigma circle X. That is GA, whatever we say. I don't get it. What notations? Okay, sigma applied on each component of X. Oh, I think this X is a kind of like the affine function, but let's see how that is being defined here. Then sigma is not a polynomial if and only for any n belongs to n. That's okay, and will not worry about it. The compact K is subset of Rn. F is in the, yeah, this is a kind of like where we can able to find out a function F belongs to in a compact set. It is so important that we are not looking for everywhere. That is always I mention like draw this one and in a particular region, that is where the compactness comes into that. For every epsilon greater than 0, there exists a k belongs to n and a matrix and a vector, a matrix such that this happens. That is how such that g of x equal to this is our neural network. I think yesterday we have written this one like b times g of ax plus b. This one, right? Yeah, that is same. We can find a matrix A, matrix B such that it happens. That's what the universal approximation theorem comes into that. So the g of x is the target function, not f of x is the target function, g of x is the approximated function. That is how the neural function can be close to f of x for a given any epsilon region. That's what so far we have discussed. That I just wanted to give different. If you look at the different references, a different way of style of writing, you don't worry about it. All are same. Only single statement is the whatever class you choose, they are dense in the continuous class. That is what final ultimate meaning. In a single statement, you can say you don't need to think of a fancy writing all these things. You can simply say that what is universal approximation theorem in a one line, that is the class of sigma pi nets or sigma nets of the format whatever we described earlier, and those are all dense inside a continuous continuous, and you should definitely mention that in a on a compact set. You should not say just a dense. It is in a local sense. That is why I have defined very beginning, like the compact set as a whole, as a, like if you denseness is Q in R is a dense, but it is a whole global way. But that is not work here, because we always look for localness, so that there is a local density, that is somewhere density. We have to figure out, like we don't know what is going outside behavior of the function. So finally, the single statement universal approximation theorem is the denseness concept only. They have not the people, many texts, they don't use the word dense. Dense is a kind of like the more analytic analysis way of understanding. It requires a proper definition. What does dense means exactly, and what kind of densities and where, and whether it is a global that that attracts a lot of things. So as mathematics background, all of you, so you can deliberately use the dense answer. So that is why I did not, I always use the word dense rather than going the everything. Like even if you look at our Weierstrass approximation theorem, you may not find this kind of statement in our textbooks. You will get something like epsilon, or like kind of this one you may see in the statement, but I don't use that. Simply, if you know the dense definition properly, you can use it in a straight way. It says everything. It says all the things. What does dense means? Okay, that is what I just wanted to convey, that with the universal approximation theorem, that um, that is how neural networks are universal approximators, the functions which approximates almost everything. That's what theory says, but practicals are different. Okay, coming back to our things, like where we are, yeah, this one. Yeah, this one. Okay, what I will do now is, uh, from this point we will go ahead with um, the computations. How are we, uh, how are we proceeding further? Like I think we have tried this one for 2 layers, right? Or a one layer, a single layer. Okay, fine. That is okay. I will teach up a little bit the this one, like this one, whatever we have explained yesterday, this matrix language. I just wanted to go again with on a different network of a single layer with maybe 3 to 2. Then we will see what we can best do over there, like the evaluation process. For that, I need a specific neural network. Let me take a specific neural network. So this one, and I just wanted to change the color of this one so that it is defining a kind of bias node, and then uh, maybe two hidden neurons. Just two hidden neurons, and let's say another two more output neurons. So with this, if we go with this one, and let me take up some color to connect this one. It is a fully connected neural network. And especially keeping the bias with different color. And okay, it's better I will keep another one more for the bias in this as well. So we will be having the bias. So we'll work out throughout our further discussion with this. Okay. I think this is a suitable network we can start with, and what we are supplying here inside this one called x1, x2, x3. Here I don't think we supply anything. We keep something one. So there are weights sitting on them, and we have given the names. I am not explicitly writing on each edge, but I can say that wij. I is the node number. Let's say this I equal to 1, I equal to 2, I equal to 3. It is simply a bias. It is on this, like you can say here, B1 and B2. And another one more index I will keep it, so that is making sense of like what layer it is, the top one superscript, that is the one. And here also you have W on the second layer to wij. It is not exactly the second layer. I mean, there are edges from the input to hidden, and there is only one layer. I could say one, that is what single hidden layer, and these are all like just passing the inputs and getting the outputs. So this is, you can say, input layer. This is a output layer, and this one is a single hidden layer. So this you can name them, and the j's are like this is j equal to 1, j equal to 2, and the bias as well, you can keep it like bias on the first layer, and here bias on the second layer. I mean, the not second layer, the edges connecting to the output layer. Yeah, so you can say the complete details. I think that is sufficient. And what goes inside this one. I will just give that the intuition what goes there inside, like in the hidden layer especially. It is uh, it takes inputs, that is uh, you have some summation with the weights. That is what you say. That is um, sum of x's, sum of xi's with w ij's for each j. Yeah. Once that is done, then then there will be a applying an activation function that is called capital G on top of it. That's what happens in a hidden layer, hidden this one computation. Then it will come out as some outcome, and that takes up carry forwards with specific weight further. So this is let's say the outcome from this one is h1. So for the simplicity purpose, so this emits h1. The h1 is equal to this one. I mean, how h1 is calculates the, you can say this is hj. You can say that this is hj. So h means for just for hidden h, the hidden neuron, hidden layer. So for h1, h2, whatever the j varies, and it goes like this. So you have h1, you have h2. So now you have weights, everything is there, and you will get outcomes like let's say the output is O1 and output is O2. And just naming conventions close to the vocabulary, so the symbol, so that it would be easy. Okay, yeah, that this is the description of complete single layer, single hidden layer neural network with two neurons in the hidden and R3 to R2. Yeah, fully described network. Now take a pen and paper and quickly write up a matrix for this. The function format, like matrix language format yesterday, what we discussed. That f of x. And tell me final answer. So in general, if you wanted to look at what is O1 equal to, H1 we have already written below, Hj in general. O1 you can write up like, how do you write up O1? What it is attracting O1? O1 is taking the inputs from this H1 and H2 from the bias. So linear combination of H1, H2 with their weights, and as well as one with this weight. Okay, so that's, you can say like H1 times W11 plus, that is for this one. You are combining H1 with this weight, and this one with this weight, W21 on the 2 with this H2 weight. So that is H2 with W21. Okay. Then finally this component with B1 2 with 1. That is just a B1 plus B1 on 2. Now if you actually apply any activation function even here, some other activation function. Here you have applied on the G and in this layer you have applied a G, and if you apply some other activation function here, and you can take up that into consideration. For time being, I will keep it CMG as well. Yeah. Then this is a O1 completely, and O2 comes with the same. Now with O2 is taking the input from this one, this one, this one, all the three. So the respective weights changes now. So that is H1 with W12 of 2 plus S2 with W22 of 2 plus D2 of 2. Now you can convert these two vectors or two components into a vector format as well. Like if you look at here, W11, W21, W12, W22, and you can think of like a matrix, and respectively they are H1, H2 are multiplying, so there is H1, H2 linear combinations. So convert that into the matrix. That is what we did yesterday, and tell me that final matrix expression. So if you write up that O1, O2 final answer, like this f of x, right? Finally, this is a O1, O2. Output O1, O2. F is a taking from R3 to R2, so that f of x equal to O1, O2. That is if you write up like g of I will just take a copy paste from here. This one, and yep. Now you have this g f of x is written this way. Now convert that into the matrix format. Yeah, tell me what is the matrix here. You can keep the g outside as g is acting on the component wise. So this one would be W1102, W212, W122, W222. Am I correct?
Yes, sir.
Yeah.
And
This is
H11, H1, H2,
H1.
then
Yeah, there is something like here I'm not keeping something like there are, I think these are two. The superscript indicates the edges of which oh, I think these are not for this one. These are the okay. These are the just H1 is to the not okay. So this superscripts are doesn't require here. These are the outcomes of the hiddens. Yeah. Yeah, yeah fine. H1 is to and plus there is B1. This one comes with the B2 with this one, and the G applies overall. So again, this H1 H2 is again a matrix. What is the H1 H2? Now tell me what is H1 H2. That is what I am going from backwards. You think of it like we are assuming H1 H2 and O1 O2 we have expressed, and now the f of x is a O1 O2 that is written like this, and matrix language it gives this one, and H1 H2 is again a matrix format. And now tell me, so what is this H1? Again, matrix comes there. Tell me what is H1. You have to do it. What is H1 H2? Tell me. I will write up. Again, this comes as a G.
Yes, sir.
Yeah, this one.
Yes, sir.
Only.
G of
G of.
G.
Yeah.
Yes, sir.
G of. Yeah.
2 cross 3 matrix, sir. W 2 cross 3
Okay.
matrix, sir. W11
W11.
to W21 to Y, sir.
W21.
Yes, sir. W31
W31. Okay. Next.
then, sir, in second row, W12
W12.
W22
W22.
W32
W32. So it
then
is a 2 cross
2
3.
cross 3
Yeah, 2 cross 3. Yeah. Then
then 3 cross 1, sir. X1 X2 X3
X1, X2, X3. Yeah, fine. With the
then
bias.
yes, sir, with bias
It will
should
be,
be to
yeah,
yes, sir. So B1 B2.
B1, B2.
Yes.
Yeah, fine. So now if you plug this one here, then again this is then it is a complete expression. So you can see this is sitting there. This what is sitting here. Mm, okay. So this then it would be a complete expression if you write that one. Like now let us name these matrices. This one I can name this one as a capital W, capital W on the 2, and this matrix I will name it as a capital W on 1. The weight matrix sitting between input to hidden, and the weight matrix sitting hidden to output. And this I will keep it as a H bar, the hidden vector, and this one is a bias onto. These are all vectors, and this one is B bar on 1. This is a vector X bar, the input. So now if we compactify this f of x, so f of x now comes with um, g of w2 h bar plus b bar. Okay, I will write up this h bar. Okay, I'll just find it. This h bar b of 2. Now if we expand, if we keep everything together, w2 h bar is again, it is a g of uh, g of w1 x bar plus b bar. So this is f of x. The complete all the things were matrices and vectors. So each of their respective shapes and sizes maintains the way the architecture goes. So I'm not mentioning the dimensions of the matrices and vectors as it takes place um, from different vectors. This is just simply in general. So whatever single hidden layer you choose, it will come into this expression only, but only the shapes will change up.
Sir, I think B bar 2 is missing, sir. Plus B bar 2.
Right. Yeah, I think that could be. Yeah, yeah. Thanks. This one plus b bar 2. Fine. Yeah, this is final f of x is this one. So uh, So the dimensions, yesterday as I explained, the dimensions of the W matrix associated here, the matrix sitting on this matrix W2, the matrix here in W1, the dimension goes this way. The dimension of W1 is a 2 by 3, and this one it goes with a 2 by 2. So always this with this one, this by this, and again this by this, that by the linear transformation. Okay, that's it. So now you should comfortable to write up matrix way of representing any neural network by this time of any size, or and you try for another layer. That is, again it will adds up another one more composition to it. Another one more. Here you can see there are two compositions, and you will see another one more composition within that, and with another one more weight matrix comes there with the similar pattern. The same patterns are going ahead, and if you closely observe it, the same pattern is repeating. Okay, whatever is sitting inside, and that is repeating the same, and another one more comes adds into it. So this should be fundamental, and you should write up in a clear way of representation for any
Sir,
neural network given. Yeah.
sir, why in this neural network, sir? Why we apply activation function in last layer also, sir?
That's I'm not mentioning as of now. Like, we don't need of that. Depends on the problem. Some problems requires it. Some problems doesn't requires it. And that's why I just keep it in general, so that if you are the G same G, like you can modify with the G, and you can give the G1 G2 as well. So you can change G1 on the one thing, G2 on the something, and mostly some problems like softmax mostly use it in here. There is something called softmax. We'll come to discuss all those things a little later. Various versions of problems, we squeeze the output. We require only the binary, or we require only a range of numbers 0 to 1, or some minus 1 to 1. For that we need to apply something so that it comes to the range of output what we are looking for. Otherwise it will just give some numbers inside Rn. So that's not our desire. So in digit recognition, we are looking for the probability values. So that probability values, we always look for something like in between 0 to 1. So we need to bring somehow the value 0 to 1. That is possible when you take a suitable activation function here, so that brings the outputs belongs to 0 to 1. So that is how we change the activation functions. So sometimes we apply on the most of the regression problems, we generally don't apply activation on the last one, and for some special cases, even in the regression with a particular restrictions, then we do take care of the activation function at the last layer. Yeah. Okay, so that's why in general we mention it in the expression, but you are not applying it. That means you take the as identity. If you are not doing it, means G1 is just simply the identity, so that it is not affecting any activation function. Okay,
Okay.
fine. Now this is so far, like, if you know something, and if you give me some numbers 1 to 5, from the F is from R3 to R2. So given any weights, we don't know as of now. These are all like arbitrarily chosen in these weights, and then you will get the answer O1, O2. You just simply pass them and get the answer, some output Y1, Y2 for this one. 125 or whatever. So here the computational items, what we don't know is these are all like the weight matrix and B1s, B2s, and these things we don't know. These are all like the weight sitting on the edges. Now the task is yours for 5 minutes. Compute number of parameters on a neural network with the neural network with the single hidden layer. That means how many parameters we need to train. So what is the training means? The training I will define formally a little later. But I will just we need to come up with what we are achieving. This is a function f of x, and now what you are saying, you have some target function g of x. You need to figure out this f of x which is close to g of x. So g of x is your solution of your problem you are looking for. You don't know what is exactly g of x, but if you go close to g of x, um, by using this f of x. This f of x is a kind of like sequence. This f of x, like if you change this some w weight on this one, it is a different f. If you change some weight here, and it is a different f. So if you modify all the weights, and these are all parameters, for every change in each parameter, it is a different f. And now the closeness to g of x is defined by these weights only. How close you go to g of x comes by picking up right choice of these numbers, the weight matrix as well as the bias vectors. These are the only few numbers, bunch of numbers which we need to figure it out. That training means predict or capturing those weights or parameters. So you might hear like some of the big neural networks or models use these many billions of parameters or thousand billions or 100 billion parameters. You might have heard in the news like how they train up those things. Those are the computational part that depends on the problem. How do you compute in a single hidden neural network? How many parameters are there? It's a simple mathematics. You can think of like how many are there. That means the number of lines here, right? And that is the number of lines. How do you come up with the number of lines? Suppose if you have n inputs and m outputs and k hidden neurons. So then, what is my answer for my question?
n plus m into k.
N plus
N plus m plus 1 into k.
okay, n plus m plus 1 into k. Is it? I don't know exactly the answer. And
Yes.
Sir, k
yeah,
into bracket में n plus m plus 1 sir. If only one hidden layer sir.
yeah, only one hidden
One
layer only. That is what I'm single hidden layer. That's what I mentioned. Yeah. Yes, tell me what is your answer?
sir
The
k
same
into
k
yes sir
into
bracket में n plus m plus 1.
same answer. Okay, I thought different. Okay, so now you generalize this one for so every time when you develop a model or neural network, you always think of the how many parameters you are using it to train up, and so that you can think of like computational efficiency, whether you should go for a cpu or whether you should go for gpu to train up because you always finally these parameters should sit somewhere in the memory. So that memory should be available. You can't take deliberately a long neural network and asking the computer to do it. That's the hardware limitations also you could take care of it, so that this number always, keep in touch with your memory limits. Okay. And there are a lot of other things to and discuss with tensors and all. That's computational things. As those things, no? Now let us. The another part is now what we do. How do we get these parameters? That is what we address now. How do we set the right choice? Right choice of parameters uh, parameters, of course, uh, for a suitable target function.
Sir, I have one more doubt, sir.
Yeah.
Sir, like for any given problem that, as you said, like GX is our solution. Just
Yeah.
how we can decide, sir, ki how many number of hidden layer requires for that problem?
Okay. Yeah, these are all called, hyperparameters. Like the number of this, not just that hidden layers, how many layers required, and each layer how many how many neurons are required. These are all called, hyperparameters, and these hyperparameters again we need to optimize. So so the right choice of the optimal choice of number of parameters, I mean the hidden neurons, or a number of layers, you then there is optimization of neural networks. Like if you take up, this is a one neural network and architecture. If you take another one more architecture with three neurons, if you take another one more architecture with three neurons, and let's say you are varying for k the number of neurons, let's say for at least 5 to 5000. It is for the assume purposely, and for somewhere in between these two, a particular choice of neural point or a threshold, a range of numbers will give good results. That is, gives a close to g of x, and maybe some of various other parts. Like you take too large, it may not work. If you take too short, it may not work. It may work, but you don't see a, the closeness, precision, whatever you want, the epsilon, you may not go to that one. So to get a particular precision, it is theoretically we can come up with this one, but practically in the target function, usually the sitting inside in a rough scale means that data which we train, that is ultimately what we train, that is not generated from a smooth function, of course, unless you simulate directly from the smooth function. So if in such cases we have to compromise ourselves the certain epsilon, that you cannot go beyond that. You cannot expect a arbitrary precision in theory, as we say epsilon. That is not possible in this one. So in our case, like as you asked, like this optimal, whatever choice of k you choose, that beyond a point we cannot go ahead. And so what for every choice of k you need to compute. Let's say you have, let's say k 1000, and for every choice of uh, hidden neurons, there must be a optimal epsilon 1, epsilon 2, and so on, epsilon 100. And what epsilon choice is giving you best approximation, you pick up that number. That is called hyperparameter tuning. So you are training training your data over several neural networks over a hyper tuning. This is what it requires a long time of computational time, because your problem is solving not just on a single neural network, and it is solving on a several architectures of the neural networks, and it is trying to pick up not just the parameters of sitting between this one. It is also trying to look for different architectures and picks a right choice of. I think I have given a kind of like yeah, this one, um, this one, the the topological structure. These are all like hyperparameter tunings, generally called. We need to tune up what choice of this one, that comes by training procedure and pick up right choice of numbers. So that's called as a advanced version of training procedure called hyperparameter tuning.
Okay, sir.
Yeah.
Okay, sir.
So yeah, you these things, you have to first develop ANN properly. Then you pick up target function and look for what choice of f of x sitting inside the sigma n is close to g of x. That these are all computational hurdles. The theory says very smoothly, like there exists f of x which is close to g of x, but computations are not so easy. Yeah. Now the coming to this point, like how do we set right choice of parameters? For time being, forget about the hyperparameters. That is, we'll see in the practical point of view. Now, the theory or algorithmic point of view, how do we set right choice of parameters? Like how do we compute this one for a target function? As of now, you don't have any target function. So what do you mean by target function? First of all, you should understand what is this target function.
So whatever we want to approximate, sir.
Yeah, okay. So that function is in general, we don't know. Even that function, if we don't, if the function we know, then we don't need a neural network. In general, why do we use neural network? Because we don't know what is that function. Let's
Yes, sir.
say
Like
some,
in
yeah, like suppose you have a machine in our classroom, and that recognizes who is speaking in the classroom. Like it recognizes voices and tells you who is speaking. Like you speak in front of that machine and it tells that your name. And by recognizing modulation, your voice pattern, and how do you speak, and how is your vocal vibrations, the modulation or whatever, the features of the voice, it predicts, and that is a function, the machine. So if you wanted to embed that software into that machine, so you need to train our voices first. That is a function. That is that is abstract function. So that you need to train up. Then what you have to do, you need to take the samples of everyone's voice, and and keep it in some class of functions and neural network, and train that voices. That is here in this case, what is the target function?
that machine, sir, like how it recognize the voice, sir.
Yeah, the voices are the target function. So so you speak to the machine and it gives the names of it. Like so, the target function is you need to train for the voices with who is speaking that voice, right? So for that, you need samples of data, and who is speaking with that data. Then you keep that feeding into that information into the neural network, and says that this voice is by so and so person, and give another information, another sample, and mix the samples with everyone's and pass through this f of x several times. So every time what happens, these weights edges on them. So they will try to come up with some closeness which matches the features of one with the voices, the names with the voices. So that is how the relation between the inputs and outputs, the mapping of inputs and outputs. It establishes a relationship between a functional from one domain with other domain. That is one Rn to Rm in general, Rx to Y in a topological sense. So this is what in general we say like pattern recognition. So finally, it is recognizing some way of patterns. Module Y, in case of voice, it has its own patterns. In case of video or visual, it has its own patterns. In case of something else, everything has its own way of patterns. So it recognizes the patterns and mapping between the patterns, mapping between one domain with other domain using the understood patterns. So this does job very well if we provide enough information to the neural network so that they can able to come this weight associatively close enough with the pattern recognition. So yeah, now we need a procedure. We need a procedure to find out or come close with these W's or the weights biases inside this one. This is usually called as a back propagation. Yeah, I don't know what's word exactly, backwards process or back propagation. Some text follows some notations, but it is a why back propagation. The name has a different meaning to it. So yeah, so now you have inputs and you have outputs here. So what is happening here? Like when you pass the inputs and when you get the output, and you are checking this output with the known answer. Let's say you have a T1, T2 as your target answer. So you should know the sample records. The sample records means that the data which you have with you, it has its own answers as well. If you don't know, if you don't have data, then in this case we cannot proceed with this. So for this it is called mostly it is a supervised learning. We will see different ways of learning, supervised and unsupervised, reinforced. That's later. Before that we'll discuss. If you have a data and it has its answers as well already, then you will check with the outcomes with how close with these answers with the target answers. So the difference between the actual answer which you are supposed to get it and the neural answer, you take it as a difference. That's as a error. That error you can call it as like it is a E1 here or E2 here. That is kind of like you can name it as uh, like T2 minus O2 or here T1 minus O1. These are the errors. So now you think of it, why this error happened? This error is happened due to the weight sitting on them. If you choose the right choice of weights, and I do not say that the error definitely goes zero. That's a foolish thing to say at every time, unless the neural network is exactly predicting the input and output. That is called saturation point or some overtraining. That we will see. There are several class of things we will discuss after seeing all the mechanisms. So now this E1, E2, uh, this E1 and E2 are the errors associated with the target and outputs. Now, what can we do with these errors? We take the advantage of these errors and look at these weights. Now, what weight you should change so that the error will come down. So if you change arbitrarily, take a particular edge, and if you let's say this is the some weight it is sitting here, and if you nudge either left or right, you can see that either the error is either reducing or increasing, right? If you nudge a particular weight, and if you take another weight, and if you nudge either little bit plus or minus, if you move around from the point, and this error may be some one direction may increase and other direction may decrease. And the way how do you choose these many changes such that this you come to a particular like think of all these are meters of the weight meters, and they are all sitting at some point, as you see in the our what is that Desmos. There we slide our bar and its error gets changes. So how do we nudge to a particular fixed position so that beyond that those are the set of suitable values, and which is that is the point that is the very optimal. Below that, with that setting, these are all settings, like let's say these are all settings, and what right settings will give you the least error. These are all weight meters, W11, W12, whatever, all those the weight sitting on the total, what you say, n plus m plus 1k uh, nudges. So here, uh, now these are all variables only. These are all variables only because of you are varying it. So you are varying them. You are varying it the variable. So now think of it in the perception of the function. This one E1 and E2 are the functions of this one only. So because of this is a let's say this is some kind of, I don't use FG, we are using for some purposes. Let's say some I don't know anything we left the notation I want. So okay, I will choose some Greek letter. Otherwise, yeah, some C or phi. I will use phi of W11, W12, and so on. All these parameters, including bias parameters, not just the weights, and including these things as well. All these are weights, of course. Uh, is a the our error E1, E2 is a function of these things. So you are getting E1 comma E2 based on these changes. So there is a function phi sitting, and which is giving a the error thing. So now your target is to look at this function, and this function is sitting inside the higher dimension. The dimension is something like the number of parameters is its dimension. Those many variables are there, so those many the function phi is sitting there. and within that parameter setting, within that dimension, you have to look for the right choice of the weight so that this E1, E2 is a least one. So this is a, now it is becoming a optimization problem. So minimizing, or you can write up something like you can write up argmin. You are looking for the weights argmin of argmin of what the domain is argmin of phi of w. I will keep it this all vectors as w bar simply in a single the vector dimension. That this w bar is the all weights argmin of this w bar. That means I am looking for mm, the right choice of vector w bar. W bar belongs to uh, W bar belongs to the dimension whatever that is n plus m plus 1 time k etc. I am looking for the right right choice of settings. That is what mathematically we can say this one. Armin of this function. So this function phi, it is difficult to manage if you keep the errors as this one. So what we do, you don't take the errors as individual components because you change a W1 and one component will come down, one component will go up, and it will, you don't know how to control both the things together. So instead of doing keep together, keeping separately E1, E2, you maintain a function where it reduces to a single number, E1 and E2. That is generally called as a loss function, E1 comma E2. So it reduces. Loss function is a function which is whatever dimension R and 2R. This loss function takes up. So it is now it is a real number. Now we are looking for the least number for where for which value of w bar this phi, the function phi, gives the least error, the least loss value. That is what we are targeted for. So now after converting that linear algebraic sense into the errors into this function that we need to travel. Okay, uh, so so how do we find out this one? Then once we know that one, that argument, the W bar, then we are done. This is the setting. This is the setting of um, the problem. So what do you say? So let us define with the loss function first of all, a particular loss function. Loss function usually I'll take something like there are a lot of loss functions, but let us use mean squared loss. The mean squared loss is something like t. You have the 1 2 in general you may have tk or tk minus ok, that is the error. Okay, I will write up ek. K is varying from 1 to m. I am writing in general m. Usually the m is the output dimension. EK, but not just the sum. Some may be sometimes errors may be positive or negative, so they cancel out. So we take the square sum of the errors, so that you will be having the sum quantity. You are keeping it like scaling them to square times, so that it won't be having any issues. That is mean squared sum. Like this, you can express as tk minus ok square, of course. So you have a function now. Now you think of it like now this function, loss function is phi. That means your phi is w bar vectors is this one now, a equal to 1 to m tk minus ok whole square. Now you can ask me, you are keeping several dimensions, that is all the weights sitting on the edges, and now this is just a real number where these are appearing here. Of course, they are sitting inside this one. Okay, I don't think it's completely depends on these W's, but we don't see directly because this OK is the output comes from the neural network using all these weights, so that this is a implicit expression where it is having all the w's inside. So now if you express this OK with this one, then this one is right, and this OK is this one, this one where all these are there. So your loss function or your function phi is actually the loss function is actually depends upon the all the weight sitting inside it. Now, now you should know strong fundamentals in the calculus. So what calculus says? What Leibniz or Newton, the great this calculus developers.
So we have to minimize this function, sir.
Yeah, minimize the function. Minimization comes with let's say the dou phi by now dou the rate of change. Why are we doing this one? We are looking for the what change in the particular weight is wij is the rate of change in wij, the change, the slight movement or slight change in wj, that is delta x or delta wij. If you change, and what change is happening here in the error, delta e. So that is what like you have wij particular weight on a particular dimension. You have lot of variables sitting inside this dimensional space. So now how do you derivative it? So this one is dou by dou wij of this one. Something like tk minus ok whole square. Yeah. Let me just yeah. So do the derivative. I see you should be very strong by this time. The all basic mathematics, the calculus, derivatives, integrations to apply. You may know them. I'm not saying that you don't know derivatives and integrations, but in the point, in the level of applying into the advanced technologies and the applications, wherever you see, yeah, not just the mathematics, and mere like just not just the a problem and solution. You know,
Sir,
now
sir, can we represent like this one is a metric form, sir. Remove the summation, sir. Can we do like that, sir? Like TK is a one column matrix, OK is a one column matrix.
No, no. TK is a number. OK is a number.
Yes, sir. Then
Yeah.
we can form a one matrix of M cross 1, where all the true values come, sir. Like T1, T2, T3, Tm. Then again, O
Yeah.
is a one matrix O, which is M cross 1, where we put all the optimized value O1, O2, O2, O3 till OM. Then take the difference and then square. And if we do that like that, then we can do the, I think, differentiation. Otherwise, we can, sir, take our differentiation inside the summation also.
Well, I'm not saying I'm not coming to which way you do it, but and there are many ways. Many people follow different strategies, but you finally you should come up with finally what we are doing. Finally, we need a formulation. That formulation we should give it to the computer so that computer will compute it. The, that's right. Like we need a because we can't say directly that this one and give this one and computer don't do it anything. You supply data, TK, okay, and how do you? We need to give some formula. Like as we for this one we have come up with a right formula. We can give it very nicely to the computer to come up with to compute f of x for given x. This is very guaranteed. And when we ask to compute the error for given any answer, or the error we can compute it, of course, no problem. But for which point the error is minimum, we don't know the formula. That formulation we need to give it to it. That is what we are trying to do it. So now proceed with the steps and come up with some formulation. I'm not saying which way you do it. Let's try for some time. I because you have to push our things here because this is not a conceptual thing now. This is a mere a calculation or evaluation point. Right, take pen and paper. I'm not saying that it is impossible. It is simple, but you have to apply our calculus very strongly. Are you trying and take pen and paper and try whatever thoughts comes to your mind, like your applications of differentiation. Okay, you try for some time this one. Maybe next time we will discuss further. From I would like to listen from you. Um, what's our trials end up and where they are arrive and does they constitute any algorithm to find out the right choice of weights by optimizing this function, this loss function. So once you're confident enough, then you can go with the algorithm to develop a training procedure. This is the only thing. Once we finish this one, then the module or the procedure is ready for keeping inside a computer so that it does we can train the data. We'll see this one from your perception from the next class. And when is our mid-sem exam for this neural network? No. Okay. When is our mid-sem exam?
Sir, from Monday, bro. Next Monday.
Next Monday. When is our exam? This neural network. Monday, first day itself or Monday? Uh,
No, sir, not on Monday.
okay. Okay, then we don't have. Do we have classes on next Monday or not? Monday and Tuesday. Or when do we meet next time? When is our next class? If there is a mid-sem in between.
Sir, I don't know, sir. I think we are having minor exams also after completing our subject exam.
Okay. So there won't be class in the next week. Okay, and that's the thing you're saying. Okay, fine. Okay, then we will see next time when we meet. Like I don't know when is your exam in this neural network exactly. So that
Sir, it is on 16th, sir. Tuesday.
okay, 16 Tuesday next week. Okay, fine. Okay, then if you have any questions, you can ask me, or otherwise we will meet after mid-sem.
Sir, I have some doubt in the exercise
Yeah.
you have given.
Yes. Okay.
The first one itself, like, how do we prove theoretically, like, given a sigma net that is dense in C and
Okay. First of all, for that to prove theoretically, you should first you prove the Weierstrass approximation theorem. That's what I said. Like before theoretically proving this one, that would be easy. That will set the ground for a proof. How the Taylor polynomials are dense in C. Then in the same context, you can think of this one because it will go in the same lines. So actually, the statements what I gave you, those are not actually the proofs. Those are counter examples because they are not dense. The questions I gave you, I raised you. Those are all questions uh, should counter by giving a counter example because they fails the density. Can't prove them. They have to counter with examples. I think which question you are referring, especially particularly. I don't remember the order and the question.
So the first one where it is normal sigmoid but without bias. 5 1
Without bias. Without bias is not a dense.
Yes, sir, that makes sense, but how do we prove theoretically?
It's not a proof. It is not dense means you have to give a counter example. If you give a particular, that means what? Like if it is a dense, then you have to go for a proof. Like if it is not true, then proof doesn't give that. Like if you give an example which counters that it is not dense, that is sufficient. That means that like you give a function f and no matter whatever epsilon, not no matter whatever epsilon, there exists an epsilon or there exists an bound, you can say beyond that you can't reach that point, the target function. You can't
Yes,
you
sir.
can't
Good.
approach that function. So if
Yes.
you provide such function, that is sufficient. You can say simply a function of kind like non-homogeneous function with zero, then you can't achieve like say let's say some g h of or k what f of x equal to constant function 5. You never achieve that because it should satisfy h of 0 or f of 0 equal to 0 from the bias. If you remove the biases, you can't reach several class of functions. If there exists a function, you can't achieve a neural network, then it is failed.
Yes, sir. Sir, and third question, sir, in exercise. We have
Yeah,
to write the Python code to see the least number of hidden neurons for
this is abstract.
approximating X.
Yeah, right. I understand what you are asking. Okay, the least number of neurons. It is you the way I think the way it goes is maybe different. Like because you can't.
Sir, I tried it in Python. Like I
Okay,
tried up to 110 hidden neurons, but it isn't coming to the given epsilon like less than 10 per minute. But it should come like because it is 10, so it should come. But how do we know the number of hidden neurons? I
we
tried
cannot
till
like there
110,
is
but
no formulation for this actually. There is no formulation. Like it is a kind of and trying with several neurons until we give a desired accuracy. If we can able to reach that bound, then that is okay. That we say. But in the case of this one, uh, here also there is a matter of choice of the function and the you choose the how do you choose the data, like do you choose the data directly from the x square or you take the noisy x square data
directly from X.
directly x square directly. If you take directly x square, definitely some point of time you will arrive, but that we need to, you have to run the numbers from one to the whatever highest number you choose, and for every choice you figure out what is the best epsilon you can. So this is not a single neural network, it is a multi neural network. You have to train for everyone, everything. So if you have a k number of neurons, then that is a different neural network, and which gives you upon training it will come around to a least point of weights, and that produces a particular error. And if you change these neurons and keep continuous forever, forever in the sense like the desired accuracy, then whenever it is hitting first time, that you can say that that is the least. And also that we cannot say that absolutely this is the one, and below that you cannot achieve. That's again depends upon other factors too. What other factors? The one is the activation function you choose. Some activation functions you may come up very quickly, some activation functions it takes a long time, and other parameter is the initial guess. The initial guess is so close to the solution, then you will get it very quickly, and with few neurons, and that is also one parameter. And these influences the thing. So my question is in the broad sense of considering as many as influences, taking into the consideration. That's up to you that what extent you can think of the influencing parameters for this number of neurons will mm, take care of the least number, such that it comes into that the desired accuracy. So don't think of that like this question is a kind of a fixed question. It is a broad sense of question. Yeah, that's for the same person, two different people get come up with the different answers. But if everyone's is their own way of explaining that one. But this is not a theory thing. It's a completely practical thing. And choice of the data and number of points you choose. These are all influences. If you choose a very less number of points, then again it influences the number of neurons. You understand the parameters influencing the number of neurons. That is what I wanted to. This question motto is that to figure out the influencing situations to decide number of neurons. Got it?
Yes, sir.
Yeah. So identify and the changes. It's not a fixed thing. If you choose 1 million points, it will come different answer. If you choose 1,000 points, it will give different answer. So anything further? Then we'll meet whenever we have next time.
Sir, in the next set of exercises where we are disproving them, like giving class of functions which are not dense and coming up with epsilon.
Which
So
one?
in that, in those last ones, sir, like keeping k fixed, finding epsilon depending on k.
Actually, I don't remember to look at them.
Fifth exercise, C1, sir.
Okay, just checking.
C.
Oh, I think only 4 exercises. Okay, because you use that now.
After those exercises.
Okay. Okay, fifth one is
Fifth, sixth, and then after six you have given the C1, sir.
okay. Yeah, what is this? Oh,
How to
bracket function. Okay. Uh, Target function is f of x equal to x square. And what is the question? G is ReLU. Oh, f of x equal to x cube, right?
No, sir. Next question after that.
P, right? Okay.
J is ReLU, and for a fixed k, we have to find epsilon k. Sigma k n g, sir. That is.
Okay, okay. I got it. Sigma. Okay, yeah. Uh, Sigma k in G. What is the G is ReLU? Uh, okay. This K is hidden neurons. Yeah, fine. Target function is f of x equal to x square. Okay, find. Okay, I think target function is f of x square. F of x equal to x square. G is ReLU. Can you describe what you understand from this?
Sir, we have to prove that this class is not dense, sir.
Which
And we have to
class?
sigma k,
Oh, okay, okay.
and we have to
Okay.
come up
If
with
if
epsilon
the if
depending
the
on k.
if the okay, if the hidden neurons are the finite, right?
Yes, sir.
Okay. Yeah. If the hidden neurons are finite, this class is not dense. Yeah. Right. So yeah. Yeah. What's the problem with this?
How to come up with epsilon?
You count that like with an example, like take off something, you cannot achieve that desired accuracy. You that will naturally happens with something because after a certain stage you can't close by anything.
So, like, do we have to see it from code, or we have to
Yeah, it's from the code only,
come up
code
with epsilon?
point of view, and not from this one. Even we can say from the ReLU point of view, we can say because I not discussed what is exactly the ReLU is doing things. That's okay, but we can at this point of juncture, we can say from the code as well. You can't close by. If you take only few neurons, let's say three neurons, you can't. F of x behaves f of x square very badly. You will get only few nudges. The nudges means the linear approximation, the points the ReLU gives. You can't. You can't close enough to approximate x square in a certain neighborhood. Few pieces of ReLU will come up. The linear segments. If you apply ReLU in the Desmos, you can check it out. It will boils down to piecewise continuous functions. Those piecewise continuous functions will approximate the x square. If the piecewise continuous functions are very least in number, they can't go close to x square. You just take a Desmos and do
Okay,
x
sir.
square and do that. You will see that
It
like
won't ReLU won't work for fixed number of nodes, but if there are many, like infinite, then it
yeah.
approximates.
It's not infinite. At least a large number, then only it will approximate for the ReLU case. We don't have infinite condition in that case. Usually. So we cannot approximate with the finite number of settings. While
Okay, sir. Thank you, sir.
yeah. So, okay. See you next time. Bye.
Bye, sir.